Welcome to Engineering Knowledge. Today we are going to discuss the topic implementation of discrete time systems. In previous videos, we have already discussed direct form 1 structure, direct form 2 structure, transpose structure, signal flow graph, and lattice structure also. In this video, we will discuss lattice structure. Okay. As we know, there are two types of filters: IIR filter, FIR filter, infinite impulse response filter, finite impulse response filter. IR filter generally comprise of poles and zeros, whereas FI filter comprise of all zeros. Now, what is lattice structure? Lattice filters generally application are used extensively in digital signal processing, digital speech processing, and in implementation of adaptive filters. That's why they are very important practically. Now, to design a lattice filter or lattice structure, we have three types, because a system transfer function of any filter is having some zeros and poles. So if we have a system transfer function having all zero filter, there is no pole, then we are going to study FI filter basically, because FI filter are those having all zero filter, and it is known as lattice filter. Second case is all pole filter. When all pole filter, it means it is known as IR filters. It is also known as lattice filter. Third is pole zero filter, where we have now poles and zeros, both are in transfer function, and it is also known as IR filter. For this structure, we will study lattice and ladder structure, which we'll study in later videos. Okay. So first we will start the general expression for the transfer function, that is general linear constant coefficient difference equation for linear time invariant system is represented as yn is equal to minus k summation k is equal to 1 to n ak yn minus k plus summation k is equal to 0 to m bk xn minus k. Physically, it means that output of any filter is combination of its previous or past outputs and present and past inputs with the help of some coefficient, where AK and BK are known as filter coefficient. Now, applying the Z transform, Yn corresponds to Z transform Yz. We know the time shift property, which states that Xn has a Z transform pair Xz. Then in time domain, if we shift Xn by k, Xn minus k, then in Z domain it will be signifies that Z raised to the power minus k delay. This delay shows the time shift property, shows the shift in time. Z raised to minus k xz. So applying this property here, yn minus k corresponds to z minus k yz. Xn minus k corresponds to z minus k xz. Time shift property. In the next step, we will put the yz term in the left hand side and take out the yz common, and then divide the expression by xz, forming the transfer function, system transfer function xz is equal to yz upon xz. It has some numerator as well as some denominator, where numerator corresponds to zeros and denominator corresponds to poles. So it is a complete pole zero system, or it is a combination of pole zero, so it is also known as IR filter, infinite impulse response filter. So our present aim is to study all zero filter, that is for FI filter, lattice structure for all zero. So we will assume that we have only zeros, there are no poles. So there are no poles, then expression will become like this. For easiness, we will assume BK, that is filter coefficient, as a alpha k. So first we are going to study all zero filter or system, that is FIR filter. HMZ is equal to AMZ, m equal to 0 to 1 to m minus 1. And what is that HMZ? It is the transfer function of filter having mth order or mth degree. And when we are talking about the filter, we can also talk it as a polynomial, because it is also a polynomial. It is a polynomial. Okay, system transfer function can be assumed as a ratio of two polynomial. So if only zeros are there, then only one polynomial will be there, AMZ. Let us call it AMZ. Now in further expressions, when we call it AMZ, we are talking about the polynomial form, and when we are calling it HMZ, then we are talking about filter form or transfer function form, where m is the degree of this polynomial or order of the filter. Degree of the polynomial or order of the filter. AMZ is numerator polynomial, that is zeros of degree m. From equation 2, now we have to carefully write these equations because these will be used again and again. From equation 2, we can have that again coefficient dk is replaced by coefficient alpha mk for just mathematical convenience, because we need these two variables m and k. M is the order of filter and k is in time domain. AMZ is equal to summation k varies from 0 to small m alpha small m k z raised to power minus k, where small m varies from 0 1 to capital M minus 1. Capital M minus 1 is the maximum value of that polynomial, and it is in time domain. Remember, it is in time domain and it is in z domain. So basically these are z transform pairs. These are z transform pairs. Now further we can solve out for the k equal to 0. Suppose we put k equal to 0, then it will become alpha 0 k alpha m0, that is k equal to 0 and z raised to power 0, plus k equal to 1 to m alpha mk z raised to power minus k, from where k varies from 1 to m summation. Now first we will define the initial condition, which is in single condition, rest condition, and zero order polynomial. For zero order polynomial m equal to 0, a0z is assumed to be 1, or alpha m0 is equal to 1. That is, first coefficient should be 1. Now this will be equal to 1 and z raised to power 0 equal to 1. So this is the final expression. This is the new expression for this filter. It is a general expression and it is our assumed expression. 1 plus k equal to 1 to m alpha mk z raised to power minus k, where m is always greater than equal to 1. That is order of filter or degree of polynomial. When we are calling about filter, then we call it order of filter. When we are calling about polynomial, then we call it degree of polynomial, where m stands for in both. Okay. Now general z transform expression is hz is equal to minus infinite to infinite hk z raised to power minus k. Okay. Comparing this expression with alpha m k z raised to power minus k, k varies from 0 to m equal to h amz and amz is equal to hmz. So obviously hmz is equal to k 0 to m alpha mk z raised to power minus k from equation number 4. Comparing these two, again I have already told you that it is z transform pair. So h, when we signify this is h, we call it unit sample response. And when we call it alpha, these are the coefficient of filter. Okay, coefficient of polynomial or coefficient of filter. So when comparing these two equations, we can find out that hk is equal to alpha mk, because for values minus infinite to 0, these coefficients are 0. For coefficient m plus 1 to infinite, these coefficients are 0. So these limit minus infinite to infinite will automatically change from limit k equal to 0 to m because of these coefficients, because these coefficients are non-zero for limit 0 to m only, and these are 0 for remaining limit minus infinite to minus 1 and m plus 1 to infinite. These coefficients are 0. These exist only for these m equal to 0 to m value. So we can write at hmk. Here we have not written m because it is general expression for z transform. hmk is equal to alpha mk, where k is equal to 1 to m. So we will use this expression later, please remember it. and all the important equations are used again and again. So please note down these equations. So by equation 3 and 4, again by equation 3 and 4, and we know the hz is also yz upon xz. By taking all these combinations 3, 4 and value of hz, we have that combined equation hmz is equal to yz upon xz, we know very well, and hmz is equal to amz. We have assumed in equation number 3, and by equation number 4, 1 plus amz is 1 plus summation k equal to 1 to m alpha mk z is to power minus k, and m varies from 0, m is greater than equal to 1. So taking these two values only, these two equalities, and taking xz here by using cross multiply, then yz equal to xz into here xz always, and this is the expression for yz, that is z transform of output y. Taking inverse z transform, we get yn is xz corresponds to xn, and this shifting property again applying, xz is multiplied with z is from minus k. By shifting property, it becomes xn minus k. Okay, so this is the expression for output of an all zero system, where xn is input and output of an all zero system. Okay, we will further use multiple times this equation, please remember it. Now we will assume that first we will put m equal to 1, that is for first order filter. M equal to 1 signifies three things. Again, I have repeated already. It is polynomial AMZ of first degree. If m equal to 2, then polynomial AMZ of second degree. And m equal to 1 signifies again filter HMZ of first order, or because it is all zero filter, it is all zero system, so it is m equal to 1 signifies that single zero, m equal to 2 signifies that double zero, you have 2 0. Okay, so it is m equal to 1 single zero system, single zero filter or system. So remember, m equal to 1 has three nomenclature. Now equation 5 will become, after putting m equal to 1, m equal to 1, k varies from 1 to 1, that is only one value, xn k m equal to 1, alpha m 1, k is equal to 1, again xn1 1. So equation will become this one. Okay, so this is the first order filter or first order first degree polynomial AMZ, and it is known as coefficient of filter or coefficient of direct form realization or coefficient of polynomial, this polynomial. Okay, so alpha 1, we can realize this equation. Previously in direct form structure we have studied in detail. Then xn is added with its delayed version, xn delayed by z inverse, that is single delay, multiplied with alpha 1 1 and added together forming yn. This equation is in direct form structure, is simply realized by this structure. Okay, now alpha 1 is the filter coefficient, remember it always. But in lattice structure we have different coefficient. Basically it is only difference between lattice structure and direct form structure, these are the coefficients. So for lattice structure we assume for zeroth order, suppose f naught n is equal to xn, g naught n is equal to xn, that is zeros order. We have defined two functions f and g, and for zero order these are input, and output yn is equal to xn, that is input. For zero order there is nothing, a simple straight line from xn to yn. For first order basic, and now iteration starts, f1n is equal to f0n previous value plus some multiplier k1 into second previous value, g0 n minus 1 delayed value, and this k1 is known as reflection coefficient of lattice or lattice coefficient. We define second function g1n again, just reverse polynomial you can say, because now k1 arises in first form, k1 f0n plus g0 n minus 1, and for these two values we have output yn equal to f1n. This is the output equation basically. For second order again the same iteration, f2n is equal to f1n, that is previous value. In this case previous value was f0n, in this second case, previous value is f1n plus multiplier, that is the lattice coefficient k2 into delayed previous value g1n minus 1. Similarly for g2n, that multiplier will come in first value k2 f1n plus delayed again second value, and the output is now yn is equal to f2n, latest second order, then latest value. And here k2 is equal to alpha 2 2, where k1 is equal to alpha 1 1, where alphas are filter coefficient and k's are lattice coefficient. It is the relation between filter coefficient and lattice coefficient. In the third order, again the same iteration, f3n is equal to previous value f2n plus lattice coefficient and delayed value of g2n minus 1. Again g3n, lattice coefficient k3n for the third order, and f2n plus g2n minus 1, and yn is equal to f3n, and k3n is equal to alpha 3 3. By generalization this lattice structure, we can have the general value fmn is equal to fm minus 1 and previous value plus km, lattice coefficient of mth order, because we are talking about mth order, gmn minus 1 delayed value, and n minus 1 previous value and delayed value. This is the previous value and this is delayed value. And third, gmn is equal to km fm minus n, fm minus 1 n plus gm minus 1 n minus 1, and yn is equal to fmn current value, present value, mth order value, and km is equal to alpha m. You can check out here, and you can pause the video and study it carefully, because this is very important slide and we will call it again and again. Again you can summarize these values. You can summarize these values because we will call it again and again. Okay. So by equation 3 and 4 we have this already done. Okay. Now what is the relation between the reflection coefficient of lattice, relation between that is a lattice coefficient k's and filter coefficient or coefficient of direct form realization, that is alphas. We call it filter coefficient or direct form realization coefficient, all are same. We can call it k's lattice coefficient or reflection coefficient, all are same. So what is the relation? You can establish a general relation. Further, suppose for m equal to 1, lattice structure says f1n is equal to, lattice structure says f1n is equal to f0 and this structure. So f1n is equal to f0n plus k1 g0 n minus 1, and k1 is equal to alpha 1 1, and direct form structure says that yn is equal to xn plus, from equation 5 you can see equation number 5 we have already noted down that equation number 5 is very important. This is the equation of number 5 for output of all zero system, and for m equal to 1 we have already arrived this equation. Okay, we are writing this equation here. This equation is same. Comparing these two values, we can find out that f0n was xn, g0 n minus 1 was xn minus 1, because f0n and g0 are both same. Okay. So comparing these value, alpha 1 is k1. Okay. First order coefficient, first order reflection coefficient, and first order lattice filter coefficient. Now second order, for second order m put just m equal to 2 in that equation in number 5. Equation number 5 you can put in, again we have this equation number 5. We will put m equal to 2 here, m equal to 2 here, 2, and ky is from 1 to 2, ky is from 1 to 2, you can check out, and equation will become like this: xn plus alpha 2 1, xn minus 1, alpha 2 2, xn minus 2, two summation values. And for second order we have the lattice structure form f2n is equal to f1n plus k2gn minus 1, and for we know that the second value of f1n is g1n. It was again for the first order value. So using these two values we can put in f2n and check out f2n. What will it become? f2n is equal to, put the f1n from this equation we have put here, and g1 n minus 1 from here. N minus 1 corresponds to this, n minus 1 corresponds to n minus 2. Okay, and this is the substrate value. G1 n minus 1 corresponds it n minus 1, and it is n minus 2 because n is delayed and value is same. Now further we will solve this equation. K2 is multiplied here, K2 is multiplied, okay, and K2 is multiplied here, and then we have again remembered the initial value. F naught n is equal to xn, G naught n equal to xn, and yn is equal to f2n here because it is second order value f2n. Now put these values so that we can compare these equations. Okay, xn plus k1, this is xn minus 1, k1 k2, this is again xn minus 1 because both are same, and this is k2 xn minus 2. Okay, now taking common the xn minus 1, and we have that k1 plus k1 k2 into xn minus 1 plus k2 xn minus 2. Now it is also output and it is also output. It is in direct form structure form and it is in lattice structure form. Difference is only the coefficients. So we can compare these and we can find out that coefficients are for second order. This is 1 1, there is no coefficient, 1 1, and this is k1 plus k1 k2, and this is alpha 2 1, that is multiplier of xn minus 1 comparison, and third coefficient is alpha 2 2, and here it is k2. So comparing these values we have the result. Alpha 2 1 is equal to k1 plus k1 k2, this value. Alpha 2 2 is equal to k2, this value. Or equivalently we can also relate it like that, k2 equal to alpha 2 2 and k1 equal to alpha 2 1 by 1 plus alpha 2 2 in terms, that is lattice coefficient in terms of filter coefficient, and these are filter coefficients in terms of lattice coefficient. Okay, you can check it out. You can pause it anytime and study it in deep. Okay. Now realization of lattice structure, we have studied the lattice structure form, and then it has two functions f1, f and g. So simple, it is, again we can see the lattice form. This is the lattice form, basically lattice form for the first order, that is xn is equal to f naught n and g naught n as it was mentioned in equation, and g naught n is delayed, g naught n is delayed by a z inverse delayed, that is now here it is g naught n minus 1. G naught n minus 1 is multiplied with k1 and added with f naught n, and it forms f1n. Similarly g1n says that it is k1 f naught n plus g naught n minus 1, that is g naught n is added with f naught n multiplied with k1, this structure. Okay, and it is g1n. So it is double structure basically, and f1n is known as yn, you know, and first it is f's are known as y's. Yn is equal to xn plus alpha 1 1 xn. This is the direct form structure. This is direct form structure and this is lattice structure form. Both have different coefficients. K1 is the lattice coefficient, alpha 1 1 is the filter coefficient. Okay, for the second stage m equal to 2. M equal to 2 means we have now again introduced a second stage. This is the first stage. We have introduced the same stage here with input of the first stage will go to the input to the second stage. Output of the first stage will go into the input of the second stage, and the stage is similar, and output is f2n is equal to f1n plus k2 gn minus 1. Check out the lattice structure. This is important, I have said already. This is now we will implement this one. Here f2n is equal to f1n plus k2 gn1 minus 1, yani it means previous input and delayed multiplied with k2. So f2n is equal to f1n plus k2 gn minus 1, g1n delayed g1n minus 1 multiplied with k2 plus f1n is equal to f2n. This is the first value, and the second value g value is k2 f1n plus g1n minus 1. It means f1n is multiplied with k2 and g1n is directly added to this value and corresponding to g2n. Okay, check out please. It is two-stage filter. So for further stages we will add these value. Next stage is k3, next stage is K4 and so on, and next value is F2, F3, F4 and so on, G2, G3 and G4 and so on. Any stage may be built by using, and the mth stage, generalized form, mth stage lattice filter may be assumed as, may be taken from this general structure, that is previous value is Fn minus n minus 1 into n, and next value is Fmn present value, and Gm minus 1n, Gmn, and it is delayed always, and multiplied with filter lattice coefficient Km, and it is multiplied with lattice coefficient Km and added to n, and forming the mth stage lattice filter. So in a general form, we have multiple stages of filter depending upon the order of filter, because M is order. Okay. So for an all zero system lattice filter, general form of filter is first stage, second stage, third stage and so on. Okay, this is the G0n, G1n, G2n and Gm minus 1, F0n, F1n, G2. Now question arises, what is significance of Gn? Why we are using Gn when output is directly limited to Fmn, Fn minus 1. First main is that because it is directly used in different values. It is used in because this structure required, this output required Gn minus 1, and this Gn minus 1 comes from here. Okay, and then again further every F contribute that G, and this G requires the previous stage value. That is why we need Gn. Second most important reason is that because it is backward, actually we will study it in detail. Now we have multiple stages, 1 2 3 stages or so on, M stages, and we know that output is the last stage, Fm minus 1, and suppose, and we from equation number 5 again I have written it, yn is equal to xn, k varies from 1 to m, alpha mk xn minus 1, and it is also when we have assumed limits k equal to 0 to m, then it was 0 to m alpha mk xn minus 1. If alpha m 0 equal to 1, initial condition assumed. It was just reminding you, for any mth stage lattice filter, suppose yn is equal to fmn. This yn is equal to fmn. We know very well. Okay, so yn equal to fmn. K varies from 0 to m. K varies from 0 to n. Alpha mk xn minus k. Okay, with alpha m 0, initial condition equal to 1. Now look at this expression. It is similar to convolution sum basically. It is actually convolution sum of alpha mk and xn basically. So it can be written as yn or fmn, both are same. Yn or equal to fmn is equal to convolution sum of alpha mn convolution with xn. These are convolution basically. Further we know that alpha m is also hm. We know that in previous slides we have studied that hm and alpha are different values. These are transfer function, system transfer function, these are polynomial. These are just representation. If we are talking about filter, then we use h. When we are talking about polynomial, we use this term. So both are synonymous, both are same. So yn is equal to, remember, yn is equal to hn convolution xn. We know it very well previously because output is always equal to convolution of xn and hn. That is taken from here. Now it is in polynomial form simply. Remember, yn is equal to hn convolution xn. In LTI system, it is simple. So just for the polynomial part, we have assumed that this h is now alphas, coefficient of that filter, alpha mn. So just it is in time domain expression. So we have done the z transform of this expression, that is yz equal to az, amz, xz, and again the same value we have already iterated in previous slides, that alpha and a are the z transform pairs. It is in time domain, it is in frequency domain, z domain. Now again we know that yz is equal to fmz, so we have put the value fmz equal to amz using this equation. Okay, so this is very important equation basically. This is very important equation. fmz equal to amz into xz. Seventh equation number. I hope you are understanding well that it is system transfer function, that is polynomial. Now we are studying the significance of Gn now. Why we are using Gn. Okay. So reminding again the values of lattice coefficient, lattice structure for order 1, f1n is equal to f0 n plus k1 g1 g0 n minus 1, g1 n is equal to k1 f0 n plus g0 n minus 1. Just reiterating the slide again and again so that you will not confuse it. In the lattice structure we have studied this slide and it was very important. We have again reiterated this term for m equal to 1. And check out that it is when we take the coefficients, it is 1 and k1 coefficient in f's. Okay, and if it is g, then it is k1 and 1. These coefficients are also written in, it is in lattice form and it is in alphas in filter coefficient form. So it can be written as 1 alpha 1 1 and alpha 1 1 1. So note that coefficient of g1n is just reverse to that of f1n. Coefficient of g1n are in reverse order to that of f1n. That's why we use this term in reverse order, g1n. Or you can assume that you can see that f1n corresponds to a polynomial. So similarly, we have that again the term f gm corresponds to some other polynomial, say it is bm. And these are because coefficient of fm and gm are in reverse order, the coefficient and these polynomial must be in reverse order. Okay, because these are corresponding to these polynomial. We will see it.